December 19th, 2025. While you slept, something passed us by. No fanfare, no alarm bells, just silence. But here's what they're not telling you. That silence might be the most terrifying sound we've ever heard. 3i Atlas completed a maneuver today that took precision beyond luck, beyond chance, beyond anything a chunk of ice should be capable of. It used Earth like a slingshot, stealing our planet's momentum to accelerate toward Jupiter. Scientists are calling it the kill shot, not because of what it did to us, but because of what it might be planning to do next. Stay with me until the end, because what happens when this object reaches Jupiter isn't an exploration mission, it's a demolition plan. You'll want to follow this journey to its conclusion. Subscribe now so you don't miss what happens next as 3i Atlas approaches Jupiter, its true target. Space holds mysteries, and this channel illuminates them. December 19th, 2025. 6 o'clock in the morning, Greenwich Mean Time. 1 in the morning on the East Coast. Most of you were asleep. Some of you were scrolling through your phones, maybe checking the weather, maybe wondering what to get your brother-in-law for Christmas. The news cycle was quiet. No breaking headlines. No emergency broadcasts. Nothing exploded. Nothing landed. Nothing sent a signal. But something happened. Right now, as you're listening to this, astronomers around the world are staring at their screens with the kind of intensity usually reserved for lottery winners, or people who just realized they left the stove on. Because today, an object designated 3i Atlas made its closest approach to Earth. It came within roughly 1.8 astronomical units of our planet. That's about twice the distance between Earth and the Sun. In cosmic terms, that's a whisper, a near miss, a handshake across the void. Mainstream media barely noticed. When they did cover it, the tone was what you'd expect. Reassuring, clinical, designed to make you feel safe. They told you it was just another comet. They told you there was no danger. They told you to go back to sleep. And maybe you did. But here's the thing about 3i Atlas that the headlines didn't mention. Or maybe didn't want to mention. This isn't just another comet. This is the third confirmed interstellar object ever detected in human history. The first was Oumuamua, that strange cigar-shaped visitor that baffled scientists in 2017. The second was Borisov, a more conventional-looking comet that arrived in 2019. And now, in 2025, we have 3i Atlas, interstellar. Let that word settle in your mind for a moment. It means this object didn't originate in our solar system. It came from somewhere else. Another star, another planetary neighborhood, maybe even another galaxy, though we can't know for sure. What we do know is that its orbit is hyperbolic. That's the technical term. It means the object isn't bound by the sun's gravity. It's not going to loop around and come back in a few thousand years like Halley's Comet. It's passing through, a tourist, a traveler. Here today, gone tomorrow, heading back out into the infinite darkness between the stars. NASA's Atlas survey in Chile spotted it first on July 1st, 2025. But when astronomers went back through their archives, they found earlier images from June, pre-discovery data, ghost images of something that was already on its way. By the time we noticed it, it had already been here for weeks, maybe longer, moving through our solar system with purpose and precision. And that's where things start to get interesting. You see, the official story is simple. 3i Atlas is a comet. It has all the hallmarks: a tail, outgassing activity, a coma of dust and vapor. Spectroscopy shows carbon dioxide, water ice, the usual suspects. NASA says it's nothing to worry about. The European Space Agency agrees. The trajectory is predictable. The composition is mundane. Move along, nothing to see here. But then you dig a little deeper. You start reading the forums, the amateur astronomy blogs, the Reddit threads that spiral into the early hours of the morning. You start noticing that certain very smart, very credentialed scientists are using words like anomalous and unexpected and requires further study. You notice that the object's rotation period changed. You notice that it exhibited non-gravitational acceleration that standard outgassing models struggle to explain. You notice that its polarization signature doesn't quite match what we see in typical comets. You notice that some telescopes observed jets of material pointing in directions that shouldn't make sense according to classical comet physics. And then you notice something else. Something that nobody in the mainstream press is talking about. Or if they are, they're burying it under layers of technical jargon and academic caution. You notice the trajectory, not where it came from, but where it's going. After its closest approach to Earth today, 3I Atlas isn't slowing down. It isn't stopping. It's accelerating outward, past our planet, past Mars, heading toward the outer solar system. And if you plot that trajectory, if you follow the numbers, if you do the math that NASA and ESA have already done, but aren't emphasizing in their press releases, you realize something that makes your stomach drop. It's heading toward Jupiter. Now, you might be thinking, so what? Space is big. Trajectories are complicated. Objects move in weird ways. But here's the thing about gravity assists. Here's the thing about slingshot maneuvers. We use them all the time in spaceflight. Voyager did it. Cassini did it. New Horizons did it. You send a spacecraft toward a planet, not to land, but to steal a little bit of that planet's orbital energy. You swing around it, you pick up speed, you change direction, and suddenly you're going somewhere. You couldn't have reached with your engines alone. It's elegant. It's efficient. It's how we've explored the outer solar system for decades. And 3I Atlas just executed a textbook gravity assist around Earth. Was it intentional? Was it planned? Did something or someone calculate this trajectory before the object even entered our solar system? Or is this just a cosmic coincidence? A random alignment of physics and probability that happens to look like intelligent design? That's the question keeping astronomers up tonight. That's the question you won't see answered on the evening news. Because if this object used Earth as a slingshot, if it's now accelerating toward Jupiter with precision that suggests purpose rather than chance, then we're not talking about a comet anymore. We're talking about something else entirely. Something that understands orbital mechanics. Something that plans ahead. Something that came here with a destination in mind. And if Jupiter is the destination, if that's where this thing is really going, then we need to ask ourselves one more question. The kind of question that turns a quiet Friday in December into the day everything changed. What does it want with Jupiter? To you and me, 3I Atlas is invisible. You can't see it with your naked eye. Even with binoculars, you'd struggle. It's a faint smear against the background stars, a ghost in the machine, detectable only through long exposure photography and computer-assisted enhancement. But to the telescopes, to the spectrometers, to the arrays of instruments we've pointed at this object since July, 3I Atlas is anything but invisible. It's a symphony of data. Velocity measurements, spectral lines, chemical signatures, rotation rates, outgassing patterns. Every pixel, every wavelength, every photon tells a story. The first chapter of that story is the orbit. 3I Atlas has an orbital eccentricity of approximately 6.1. If you're not an orbital mechanics person, and let's be honest, most of us aren't, that number might not mean much. So let me put it in context. Objects that are gravitationally bound to the sun, like planets and asteroids and regular comets, have eccentricities between 0 and 1. 0 is a perfect circle. 1 is a parabola, the edge of escape. Anything above 1 is hyperbolic, which means the object is moving fast enough to break free of the sun's gravity entirely. 3I Atlas is at 6.1. It's not just escaping, it's leaving with authority. It came from interstellar space, and it's going back to interstellar space, and nothing in our solar system can stop it. Hyperbolic orbits are rare, but not unheard of. Oumuamua had one. Borisov had one. But here's where 3i Atlas starts to diverge from the script. Both of those previous visitors showed outgassing, but their behavior was relatively predictable. You could model their motion using standard equations, plug in the outgassing rates, account for the rocket, effect of vaporizing ice, and the numbers match the observations. With 3i Atlas, the numbers don't quite match. There's extra acceleration, motion that can't be fully explained by the gas jets we're observing. Some astronomers attribute this to asymmetric outgassing, jets firing in weird directions due to an irregular nucleus shape. Others aren't so sure. Avi Loeb, the Harvard astrophysicist who famously suggested Oumuamua might be artificial, has raised similar questions about 3i Atlas. He's pointed out that the non-gravitational forces acting on this object exceed what we'd expect from a typical comet of this size and activity level. He's not saying it's a spaceship. He's saying the data doesn't fit the model cleanly. And when data doesn't fit models, we need to pay attention. Mainstream astronomers have pushed back, publishing papers that argue the anomalies can be explained within conventional comet physics if you tweak the parameters just right. But even in those papers, you can sense the tension, the uncertainty, the footnotes that say more observations needed and alternative explanations cannot be ruled out. Then there's the rotation. Comets spin. That's normal. But 3i Atlas showed changes in its rotation period as it approached the sun. Its spin rate varied. That can happen due to outgassing torque, like a spinning ice skater pulling in their arms. But the pattern of variation was unusual. Some observers noted periodic modulation of jet activity, bursts of gas and dust that seemed to follow a rhythm, almost like clockwork. Jets that turned on and off with regularity. Jets that pointed sunward, which is backwards from what you'd normally expect. Most comet jets face away from the sun, driven by solar heating. Sunward jets suggest something more complex is happening beneath the surface. Maybe volatile pockets with different compositions. Maybe structural asymmetries. Maybe something we haven't thought of yet. Polarimetry adds another layer. When light reflects off a comet's dust, it becomes polarized, and the degree and angle of polarization tell us about the particle size and composition. 3i Atlas showed a polarization signature that differs from most solar system comets. It's not wildly different, but it's different enough to raise eyebrows. Different enough that some researchers have suggested the dust grains might have unusual shapes or be made of materials we don't commonly see in comets. Others argue the difference is within normal variation, just at the tail end of the distribution curve. Here's the tension. On one side, you have scientists saying this is a comet, just an unusual one, but nothing that breaks the laws of physics or requires exotic explanations. On the other side, you have scientists saying the anomalies are real, persistent, and deserve more scrutiny than they're getting. Both sides have data. Both sides have papers. Both sides have reputations to protect. And in the middle, you have the public trying to figure out what to believe. Non-gravitational acceleration. Let me explain what that means in plain language. When you plot an object's position over time and compare it to what pure Newtonian gravity predicts, sometimes the object is somewhere it shouldn't be. Maybe it's a little ahead of where it should be. Maybe it's a little off to the side. For comets, this happens because they're outgassing. As ice turns to vapor, it shoots out in jets. And those jets act like tiny rocket engines, pushing the comet in directions that gravity alone wouldn't explain. We can measure this. We can model it. Usually, it's straightforward. But with 3i Atlas, the magnitude and direction of the non-gravitational acceleration have been harder to pin down. Different observation teams have gotten slightly different results, Some say it's consistent with standard outgassing. Others say there's a residual component that doesn't fit the outgassing model cleanly. This is where the debate gets heated. Because if an object is accelerating in ways that outgassing can't fully explain, you have to start considering other possibilities. Maybe there's an internal heat source. Maybe the nucleus has a weird shape that focuses jets in unexpected ways. Maybe there's some exotic ice composition we haven't accounted for. Or maybe, and this is the possibility that makes some scientists uncomfortable, maybe the acceleration isn't random. Maybe it's controlled. I'm not saying it is. I'm saying that's the question lurking in the background of every technical paper, every conference presentation, every late-night conversation between astronomers who've been staring at this thing for 6 months. Because if you're an object traveling between star systems and you want to adjust your course, you don't necessarily need engines. You just need to be able to vent material in precise directions at precise times. You need to understand thrust and momentum and orbital mechanics. And if you can do that, you can steer. Is 3i Atlas steering? The data is ambiguous. The majority of scientists say no. A vocal minority say maybe. And a tiny fringe, the kind of people who get called cranks and crackpots until they're proven right, say yes. The debate is unresolved. The observations continue. And tonight, as 3i Atlas moves past Earth, as it continues on its trajectory toward the outer solar system, the telescopes are watching. The data is accumulating. And somewhere in that data, buried in the noise and the uncertainty and the competing models, might be the answer to the question we're all afraid to ask out loud. What if it knows where it's going? Let me tell you about gravity assists, because understanding them is key to understanding why some people think 3i Atlas might not be what it seems. In 1977, NASA launched 2 spacecraft called Voyager 1 and Voyager 2. Their mission was to explore the outer planets: Jupiter, Saturn, Uranus, Neptune. But there was a problem. Getting to those planets required enormous amounts of fuel, more than we could reasonably pack into a spacecraft. So the engineers came up with a clever solution. Instead of fighting gravity, they'd use it. They'd aim Voyager at Jupiter, swing around behind it, and let Jupiter's orbital motion fling the spacecraft forward like a slingshot. Voyager would steal a tiny bit of Jupiter's momentum, slowing the planet down by an immeasurably small amount and speeding itself up significantly. Then it would do the same thing at Saturn, and then Uranus, and then Neptune. By the time Voyager 2 finished its grand tour, it had visited all 4 giant planets without using hardly any fuel at all. It was brilliant. It was elegant. It was the only way to make the mission work. This technique is called a gravity assist, or a gravitational slingshot. Every interplanetary mission we've flown in the last 50 years has used it in some form. Cassini used Venus and Earth to reach Saturn. New Horizons used Jupiter to reach Pluto. Parker's solar probe uses Venus over and over to dive closer and closer to the Sun. It's one of the fundamental tools of spaceflight. You aim at a planet, not to land, but to bend your trajectory and pick up speed. The math is complicated, but the principle is simple. Energy is conserved, momentum is exchanged, and if you plan your trajectory carefully, you can go places you couldn't reach otherwise. Now, here's where 3i Atlas gets interesting. After its closest approach to Earth today, December 19th, the object is heading outward. If you plot its trajectory based on current observations, it's moving toward the outer solar system, toward the realm of the gas giants. And Jupiter is right there, not directly in its path, but close enough that Jupiter's gravity will influence the object's motion. Some analysts have suggested that the flyby of Earth might have adjusted 3i Atlas's trajectory just enough to bring it into a more optimal alignment with Jupiter. That the Earth encounter wasn't random, but a calculated maneuver. Now, before you accuse me of wearing a tinfoil hat, let me be clear. This is speculation. The mainstream scientific view is that 3I Atlas is on a natural trajectory, determined by its initial velocity when it entered the solar system and the gravitational forces it encountered along the way. The fact that it passed near Earth is a coincidence. The fact that it's heading toward Jupiter's general vicinity is a consequence of orbital mechanics, nothing more. But here's the problem with that explanation. Gravity assists are hard to execute, really hard. When NASA plans a mission, they spend years calculating trajectories, running simulations, optimizing launch windows. They're working with objects they control, engines they can fire, thrusters they can pulse, and even then, things go wrong. Spacecraft miss their targets. Course corrections are needed. Margins are tight. The idea that a natural object could execute a gravity assist by accident, that it could arrive from interstellar space with exactly the right velocity and angle to use Earth as a slingshot toward Jupiter, strains probability. Not impossible. Just unlikely. Very unlikely. Let me put some numbers on it. The velocity change you get from a gravity assist depends on the mass of the planet, the distance of your closest approach, and your incoming velocity. For a small object, like 3I Atlas, passing Earth at 1.8 astronomical units, the velocity change would be modest, but not negligible. A few kilometers per second, maybe. Enough to tweak the trajectory. Enough to turn a near miss of Jupiter into a close encounter. And if you're trying to reach Jupiter's sphere of influence, if that's your goal, then using Earth as a stepping stone makes perfect sense. It's exactly what we would do if we were sending a probe to Jupiter and wanted to save fuel. So the question becomes, did 3I Atlas just get lucky, or did someone or something plan this? And if it was planned, what does that imply? Let me walk you through the speculative scenario, and I want to emphasize that word, speculative. This is not confirmed. This is not consensus science. This is the kind of thing people debate in bars after conferences, or in comment sections at 3 in the morning, or in think tanks where the job description includes consider unlikely possibilities. The scenario goes like this. An advanced civilization or an autonomous probe programmed by such a civilization wants to explore or interact with our solar system. Maybe they're interested in Jupiter specifically. Maybe Jupiter is the mission target. They can't just launch a spacecraft and hope it gets there. Interstellar distances are vast. Travel times are measured in decades or centuries, even at high fractions of the speed of light. So they optimize. They use gravity. They plan a trajectory that uses the sun's gravity well to decelerate as they approach, then uses planetary flybys to adjust their path toward their destination. It's not science fiction. It's applied orbital mechanics. We do it with our own probes all the time. The only difference is scale. If 3I Atlas executed a gravity assist around Earth, then it means the object arrived at Earth with a precise velocity, angle, and timing. It means someone or something knew Earth would be here, at this exact point in its orbit, on December 19th, 2025. It means the trajectory was planned, possibly decades or centuries ago, accounting for the motion of planets, the gravitational influences of the sun, the tiny perturbations from asteroids and other bodies. It means the level of precision is extraordinary, beyond what we currently think natural processes can achieve. And if that's true, if even a fraction of that scenario is true, then we're not looking at a comet. We're looking at a spacecraft, or something that functions like one. Now, I know what you're thinking. Where's the proof? Where's the smoking gun? And the answer is, there isn't one. Not yet. What we have are anomalies, unexplained accelerations, unusual rotation changes, a trajectory that looks suspiciously convenient, data that doesn't quite fit the models, observations that make some scientists uncomfortable. But proof? Evidence that would hold up in court, or in a peer-reviewed journal, or in a congressional hearing? No, we don't have that. What we have is a mystery, and mysteries are uncomfortable. They're unsettling. They demand answers, and we don't have good ones yet. Jupiter is the key. If 3I Atlas is heading there, if its trajectory brings it into Jupiter's gravitational influence, then that's where the next chapter of this story will unfold. Jupiter is the largest planet in our solar system, over 300 times Earth's mass. Its gravity dominates the outer solar system. Its magnetic field is the strongest of any planet. Its radiation belts are lethal. Its atmosphere is a churning storm of hydrogen and helium, with wind speeds exceeding 400 miles per hour. If you're an interstellar visitor and you want to study a gas giant, or use one as a gravitational anchor, or tap into its energy environment, Jupiter is the obvious choice. It's the biggest target, the most influential, the most resource-rich. And if 3I Atlas used Earth to get there, if today was just the first step in a longer journey, then what happens when it arrives will define whether this story ends as a footnote in astronomy textbooks, or as the moment everything changed. The trajectory lock is real. The destination is clear. Whether it's intentional or coincidence is the question that will haunt astronomers for years to come. Let me be absolutely clear about something before we go any further. The majority scientific interpretation of 3I Atlas is that it's a comet, a natural object, a chunk of ice and rock that formed around another star billions of years ago, got ejected from its home system through gravitational interactions, and wandered through interstellar space until it happened to pass through ours. The spectroscopy supports this. We see carbon dioxide. We see water ice. We see silicate dust. We see organic compounds. All the things you'd expect from a comet. NASA says it's a comet. The European Space Agency says it's a comet. Most professional astronomers say it's a comet. And they're probably right. But there are anomalies. Real, documented, peer-reviewed anomalies that even the most skeptical scientists acknowledge. These aren't conspiracy theories. These aren't fabrications. These are observations that don't fit neatly into the standard comet model. And when you start stacking them up, one after another, you begin to understand why some people are asking uncomfortable questions. First, the non-gravitational acceleration. I've mentioned this already, but it bears repeating because it's the most significant anomaly. When you track 3I Atlas's position over time and compare it to predictions based solely on gravity, there's a mismatch. The object is moving in ways that gravity alone can't explain. Standard comet models attribute this to outgassing, the rocket effect of vaporizing ice pushing the nucleus in various directions. But multiple observation teams have noted that the magnitude of the acceleration seems higher than what the observed outgassing should produce. Some models can account for this by assuming the nucleus has an unusual shape, or that there are hidden jets we can't see directly, or that the outgassing is more asymmetric than we think. But these are assumptions, parameters we're tweaking to make the model fit the data, rather than predictions we made beforehand that turned out to be correct. That's not necessarily wrong. Science does this all the time, but it does mean the case isn't as closed as some people claim. Second, the polarization signature. When light reflects off dust particles, it becomes partially polarized, and the degree of polarization depends on the size, shape, and composition of the particles. 3I Atlas shows a polarization pattern that's unusual compared to most solar system comets. It's not wildly different, but it's at the edge of the known distribution. Some researchers have suggested this indicates the dust grains might be more irregular in shape or composed of materials with different optical properties. Others have proposed that the dust might contain a higher proportion of metallic or crystalline components than typical comet dust. None of these explanations are crazy. They're all plausible within known physics. But they do imply that 3I Atlas is not a typical comet, even if it is a natural one. Third, the jet activity. Several observatories reported periodic variations in the intensity and direction of jets emanating from the nucleus. Jets would brighten, then fade, then brighten again, following a pattern that seemed to correlate with the rotation period. That's not unusual in itself. Many comets showed jets that activate as different parts of the nucleus rotate into sunlight. But some observers noted jets pointing sunward, toward the sun rather than away from it. That's weird. Solar heating should drive jets away from the sun, like water evaporating from a heated surface. Sunward jets suggest either a very unusual surface structure or internal pressure sources that override the solar heating effect, or some other process we don't fully understand. Antitails, as they're sometimes called, have been observed in other comets, so this isn't unprecedented. But it's rare, and combined with the other anomalies, it adds to the picture of an object that doesn't quite behave the way we expect. Fourth, the post-perihelion dust tail, or rather, the lack of it. Perihelion is the point in an orbit where an object is closest to the sun. For comets, this is when outgassing is most intense, when the nucleus heats up and releases massive amounts of gas and dust. After perihelion, you'd expect a prominent dust tail, visible for weeks or months as the comet recedes from the sun. Some observers reported that 3I Atlas's dust tail was fainter than expected after perihelion, given the amount of activity seen during the approach. This hasn't been verified by all observation teams, and it could be an artifact of viewing geometry or observational bias. But if true, it suggests either that the outgassing shut down more quickly than expected, or that the dust production was less than predicted, or that the tail dispersed unusually fast. Again, not impossible. Just odd. Fifth, the composition hints. Spectroscopic analysis of 3I Atlas shows the usual suspects: carbon dioxide, water ice, some organic molecules. But there have been informal reports, not yet published in major journals, of unusual spectral lines that might indicate higher than normal abundances of certain metals or minerals. One frequently mentioned candidate is nickel, which could give the dust a different reflectance and polarization signature. Comets do contain trace metals, so this wouldn't be shocking. But if 3I Atlas has significantly more metal than typical comets, it would raise questions about where it formed and under what conditions. Maybe it comes from a planetary system with a different chemical makeup than ours. Maybe it formed closer to its parent star, where temperatures were higher and metals could condense. Or maybe, and this is where speculation really takes off, maybe it's not entirely natural. Let me unpack that last possibility carefully, because it's the one that gets people labeled as cranks. If an object contains more metal than expected, if it has structural components that look artificial under close inspection, if its behavior suggests active control rather than passive outgassing, then you're no longer talking about a comet. You're talking about a probe, a spacecraft, an engineered object. And if it's engineered, then someone engineered it. Someone with the ability to build things that can survive interstellar travel. Someone with the knowledge to plan trajectories across light years and centuries. Someone who might have interests in our solar system. Mainstream science does not support this conclusion. I need to say that again for the people in the back. Mainstream science does not support the idea that 3I Atlas is artificial. The anomalies can all be explained, with varying degrees of confidence, within natural comet physics. But explanations are not proof. Models are not reality. And when you have an object that keeps surprising you, that keeps deviating from predictions in small but persistent ways, you have to at least consider the possibility that your model is incomplete. Maybe 3I Atlas represents a new class of interstellar object, something we haven't encountered before. Maybe comets from star systems are just weirder than we expected. Or maybe, just maybe, we're looking at something that didn't form naturally. The difference between sensor noise, observational artifacts, and true anomalies is critical. Telescopes aren't perfect, Data processing introduces errors. Statistical fluctuations happen. Sometimes you see patterns that aren't really there. Scientists are trained to be skeptical, to rule out mundane explanations before invoking extraordinary ones. And they should be. But skepticism can also become dogma. The assumption that all interstellar objects must be natural can become a blinder that prevents us from seeing evidence to the contrary. Not because scientists are stupid or biased, but because paradigms are hard to shift. Because careers are built on consensus. Because saying, "This might be artificial," is professional suicide unless you have ironclad proof. And proof is hard to get when the object is millions of miles away, moving fast, and won't be back for a close look ever again. So we're left with anomalies, observations that make some people uncomfortable, data that doesn't quite fit, a story that's still being written, with chapters we haven't read yet. And the central question, the one that keeps coming back no matter how many conventional explanations we pile on top of it: why does this object behave almost like a comet, but not entirely? The answer will shape how we understand not just 3I Atlas, but the whole category of interstellar visitors. Because if this is what natural interstellar comets look like, then we need to update our models, revise our expectations, and prepare for more surprises as we detect more of these objects in the future. But if this is something else, if even one of the anomalies turns out to be evidence of design rather than chance, then the implications cascade outward in ways we're only beginning to grasp. And Jupiter is where we'll find out. Jupiter is not just big, it's incomprehensibly big. Its mass is more than twice that of all the other planets in our solar system combined. Its volume could swallow Earth over 1,300 times. Its Great Red Spot, a storm that's been raging for at least 400 years, is larger than our entire planet. When you look at Jupiter through a telescope, even a small one, you're not seeing a point of light. You're seeing bands of color, swirling clouds, a world that's alive with motion and energy. Jupiter isn't just a planet. It's a system unto itself, with at least 95 moons, a faint ring system, and a magnetic field so powerful it extends millions of kilometers into space, trapping charged particles in radiation belts that would kill a human in minutes. If you're planning an interstellar mission, if you're deciding where to go in a new solar system, Jupiter is the obvious target. It dominates everything around it. It shapes the orbits of asteroids. It protects the inner planets from some comet impacts by acting as a gravitational shield, or conversely, flings other objects inward. It's the keystone of the outer solar system. And it's not just massive, it's energetic. The planet emits more heat than it receives from the sun, a consequence of its slow gravitational contraction and the energy released as helium rains down into its interior. Its magnetosphere is the largest structure in the solar system, made by a planetary body. If you could see Jupiter's magnetic field with your eyes, it would appear larger than the full moon in our sky, despite being 5 times farther away than the sun. Mainstream astronomy will tell you that 3I Atlas will pass through the outer solar system, potentially coming somewhat near Jupiter's orbit, and then continue on its way back to interstellar space. It's following a hyperbolic trajectory. It's not going to stop. It's not going to orbit. It's going to keep moving, maybe swinging by Jupiter's gravitational influence, maybe getting a slight course adjustment, and then disappearing into the void. That's the expected outcome. That's what the models predict, and there's no reason to think otherwise, unless you start asking questions that most scientists prefer not to ask in public. What if reaching Jupiter isn't a coincidence? What if Jupiter is the destination? Let me walk you through why that idea, as speculative as it is, has gained traction in certain corners of the scientific and amateur astronomy communities. If you're an advanced civilization, or an autonomous probe programmed by such a civilization, and you want to study a solar system, You don't just pick a random target. You pick the most interesting, the most informative, the most resource-rich. You go where the action is. In our solar system, that's Jupiter. It's the prototype of gas giants, the kind of planet that dominates exoplanet surveys because they're easy to detect and common throughout the galaxy. Understanding Jupiter means understanding a whole class of worlds. Its atmosphere is a chemistry lab on a planetary scale, with complex organic molecules forming in high-altitude clouds, raining down into deeper layers where pressure and temperature conditions are extreme. Its magnetic field interacts with the solar wind in ways that teach us about magnetohydrodynamics and plasma physics. Its moons, especially Europa, Ganymede, and Callisto, might harbor subsurface oceans where life could exist. From a scientific perspective, Jupiter is the prize. It's where you'd want to send your best instruments, your most capable probes. And if you're traveling from another star system, if you've spent centuries or millennia crossing the interstellar medium, you're going to want to make the trip count. You're going to aim for the target that gives you the most bang for your buck. But there's another angle, a more speculative and, frankly, more unsettling possibility. What if the interest in Jupiter isn't purely scientific? What if there's a functional purpose? Jupiter's environment is extreme in ways that are hard to comprehend. The pressure at the core is estimated to be tens of millions of times Earth's atmospheric pressure. The temperature might exceed 30,000 degrees Celsius. At those conditions, hydrogen, which makes up most of Jupiter's mass, transitions into a metallic state, conducting electricity and generating the planet's magnetic field through dynamo processes. The energy densities are staggering. The magnetic field's strength near the poles can exceed 10 Gauss, orders of magnitude stronger than Earth's field, and the magnetosphere contains trapped radiation, high-energy particles spiraling along field lines, creating an environment that's both hostile and, from a certain perspective, useful. If you're an advanced probe and you need energy, Jupiter is a power plant. If you need to study magnetic field interactions, Jupiter is a laboratory. If you need to test technologies in extreme conditions, Jupiter is the ultimate proving ground. And if you have capabilities we don't understand, if you can tap into planetary magnetic fields, or extract energy from gravitational gradients, or do things we haven't even imagined yet, then Jupiter isn't just a destination. It's a resource. There's an old idea, more science fiction than science, called the Lucifer Project. The notion was that if you could somehow ignite fusion in Jupiter's core, you could turn it into a second sun. It's been explored in novels and movies, usually as a plot device to create drama or terraform the outer solar system. The problem is, it's nonsense. Jupiter doesn't have nearly enough mass to sustain hydrogen fusion. You'd need to add at least 80 times more mass to get to the minimum threshold for a brown dwarf, let alone a true star. And even if you could, you'd need an energy input so colossal, so beyond anything we can currently imagine delivering, that it's effectively impossible with known physics. But here's where things get weird. What if the goal isn't to ignite Jupiter, but to do something else? What if there are processes, technologies, or interactions with gas giants that we haven't considered because we're limited by our current understanding of physics? We know so little about what's possible at the frontiers of science. 50 years ago, we didn't know dark energy existed. 100 years ago, we didn't know nuclear fusion powered the sun. 200 years ago, we thought space was filled with ether. Our models are provisional, incomplete, subject to revision. And when you're dealing with an object that might represent a civilization centuries or millennia more advanced than ours, you can't assume they're limited by our physics. They might know things we don't. They might be able to do things we think are impossible. So when people speculate about what 3i Atlas might want with Jupiter, they're not necessarily talking about ignition or destruction. They're talking about interaction, observation, sampling, energy harvesting, magnetospheric research, communication relay, resource extraction, or things we don't have words for yet because the concepts don't exist in our scientific vocabulary. The trajectory suggests Jupiter is in play. Whether that's by design or accident is the question. Mainstream science leans toward accident, toward natural orbital mechanics and coincidence. But a growing number of people, some credentialed scientists among them, are pointing out that the precision required for this trajectory, the timing of the Earth flyby, the apparent lock onto Jupiter's vicinity, all of it strains the limits of what random chance should produce. Not impossible, just improbable. And when you're dealing with interstellar objects, with visitors from other star systems, improbable starts to feel suspicious. If 3I Atlas arrives at Jupiter, if it passes through its magnetosphere, if instruments detect something unusual during that encounter, then the story changes. The data will speak. The observations will either confirm it's just a comet passing through, or they'll raise new questions. And if those questions don't have good answers, if the anomalies persist, if the behavior remains unexplained, then we'll have to confront the possibility that we're not alone, that someone else is here, studying the same planets we are, for reasons we can only guess at. Jupiter is the key, the target, the waypoint, or maybe the destination. What happens there will determine whether December 19th, 2025 is remembered as a quiet day when a comet passed by, or as the day we woke up to a cosmos more crowded, more complex, and more terrifying than we ever imagined. Every time something strange happens in the sky, the internet lights up. You know the pattern. A grainy video appears on YouTube. Someone posts a thread on Reddit. The comments section explodes into a war between believers and skeptics, between people who think every unexplained light is a spacecraft and people who think even spacecraft are weather balloons. 3I Atlas has followed the same trajectory, pun intended, through online culture. Since its discovery in July, it's been the subject of thousands of posts, videos, forum threads, and blog articles. Some are sober analyses by amateur astronomers trying to make sense of the data. Others are full-blown conspiracy theories, complete with claims of government cover-ups, NASA hiding evidence, and secret missions to intercept the object before it reaches Jupiter. Let me be clear, most of these theories are nonsense. NASA isn't hiding images. There's no secret military operation. The government isn't suppressing information. I say this not because I have blind faith in institutions, but because the logistics of such a cover-up would be impossible. Astronomy is a global enterprise. Thousands of telescopes, run by universities, observatories, and amateur enthusiasts, are pointed at the sky every night. If there were dramatic images of 3I Atlas showing artificial structures or anomalous features, someone would have leaked them by now. The idea that all of these independent actors, in different countries, with different motivations, could be coordinated into silence is absurd. It assumes a level of competence and control that governments simply don't have. But here's the uncomfortable truth. Just because conspiracy theories are wrong doesn't mean the anomalies aren't real. The fact that some people are jumping to wild conclusions doesn't invalidate the legitimate scientific questions being raised. And dismissing all speculation as conspiracy mongering is a mistake, because it shuts down the kind of open inquiry that science depends on. Let me give you some examples of what people are saying online and why they're saying it. One common thread is the claim that 3I Atlas is a probe, not a comet. This comes from the observation that its behavior doesn't perfectly match standard comet models, combined with the fact that it's an interstellar object, which makes it exotic by definition. People point to the non-gravitational acceleration, the weird polarization, the rotation changes, and argue that these are signs of active control. They cite Oumuamua as a precedent, noting that Avi Loeb suggested it might be artificial and hasn't been definitively disproven. They ask why NASA hasn't released high-resolution images, ignoring the fact that 3I Atlas is small, faint, and incredibly hard to photograph in detail with current technology. Another thread is the Jupiter targeting hypothesis. People look at the trajectory, note that it seems to be heading toward Jupiter after the Earth flyby, and conclude that Jupiter must be the mission objective. They speculate about what an advanced civilization might want with a gas giant: energy harvesting, scientific research, even terraforming or ignition. Some reference the Lucifer project, even though that idea is physically implausible. Others talk about magnetospheric manipulation, tapping into Jupiter's radiation belts, or using the planet as a gravitational anchor for further exploration of the outer solar system. These ideas range from scientifically plausible to science fiction, often without clear delineation between the two. A third thread focuses on the timing. 3I Atlas was discovered in July 2025, but its closest approach to Earth occurred in December. Some people find it suspicious that the discovery wasn't announced with more fanfare, that the mainstream media barely covered it, that the public was kept largely in the dark. They interpret this as evidence of suppression, when the simpler explanation is that most people don't care about faint comets passing at safe distances. Astronomy news doesn't usually make headlines unless something is about to crash into us, or looks really spectacular in the sky. 3I Atlas did neither. Why do these theories gain traction? Part of it is human. Psychology. We're pattern-seeking creatures. We see faces in clouds, hear voices in static, find meaning in randomness. When confronted with incomplete information, we fill in the gaps with narratives that make sense to us, even if those narratives aren't supported by evidence. Conspiracy theories are compelling because they offer simple explanations for complex phenomena. They identify villains and heroes, insiders and outsiders. They give people a sense of control in a chaotic world, even if that control is illusory. But there's another factor at play, one that's more subtle and more important. Trust in institutions has eroded. Whether it's government agencies, academic scientists, or media outlets, large segments of the public no longer believe what they're told. Sometimes this skepticism is justified. Institutions do lie, do cover up mistakes, do prioritize their own interests over transparency. But often the skepticism is misdirected, aimed at conspiracies that don't exist while ignoring real issues that do. The result is a fractured information landscape where people retreat into echo chambers, consuming content that confirms their existing beliefs and rejecting anything that challenges them. In the case of 3I Atlas, this means that some people will believe it's artificial no matter what the evidence says, while others will dismiss any anomalies as measurement errors or hoaxes. Neither extreme is helpful. What we need is nuance, the ability to hold uncertainty without collapsing into dogma. We need to acknowledge that the data is ambiguous, that scientists are debating the interpretations, and that the truth might not be clear for years or decades. We need to resist the urge to pick a side prematurely, to declare victory or defeat before the game is even over. Healthy skepticism is a virtue. It means questioning claims, demanding evidence, refusing to accept explanations just because they come from authority figures. But healthy skepticism is different from reflexive denial or conspiratorial thinking. Healthy skepticism says, show me the data, walk me through the reasoning, and I'll judge for myself. Conspiratorial thinking says, I don't trust you, so anything you tell me must be a lie. The first is the foundation of science. The second is the death of it. There are historical analogies worth considering. In the 1950s and 60s, UFO sightings were common, and many people believed the government was covering up evidence of extraterrestrial visitors. Decades later, we've learned that some of those sightings were classified military aircraft, some were misidentified natural phenomena, and some remain unexplained. But none have been proven to be alien spacecraft. The UFO phenomenon is a mix of real observations, measurement errors, hoaxes, and cultural mythology. 3I Atlas could follow a similar path. It might turn out to be just a comet with unusual properties. It might turn out to be something we don't have a category for yet. Or it might turn out to be evidence of something truly extraordinary. We won't know until the story is finished, and the story is far from over. The debate around 3I Atlas will be studied seriously, regardless of the outcome. Astronomers will publish papers. Data will be archived. Future observations will refine our understanding. If it's a comet, we'll learn more about interstellar objects and update our models. If it's something else, if the anomalies persist and new evidence emerges, then we'll have to confront a paradigm shift. Either way, the process of inquiry, the willingness to ask uncomfortable questions, and follow the evidence wherever it leads, is what separates science from mythology. So yes, there are conspiracy theories swirling around 3I Atlas. And yes, most of them are baseless. But buried within the noise, within the speculation and the wild claims, are legitimate scientific questions that deserve serious attention. The challenge is separating the signal from the noise, the data from the narrative, the possible from the impossible. And that challenge, uncomfortable as it is what makes this story worth following. Because whether 3I Atlas is a comet or a probe, whether Jupiter is a coincidence or a target, the questions it raises about our place in the universe, about the nature of interstellar objects, about the limits of what we know and what we don't, those questions are real, and they're not going away. Let me pull the camera back for a moment. Let me zoom out from 3I Atlas, from its trajectory and its anomalies, and its trajectory toward Jupiter, and talk about the bigger picture. Because this object, as fascinating as it is just one data point in a much larger story. The story of how our understanding of the universe is changing, not gradually, but in sudden, disorienting leaps that leave us scrambling to keep up. Astronomy is in the middle of a revolution, and most people haven't noticed. In the last few years, we've deployed telescopes more powerful than anything that came before. The James Webb Space Telescope is sending back images of galaxies that formed when the universe was only a few 100 million years old, showing us structures and star formation processes that challenge our models of cosmic evolution. The Vera Rubin Observatory is about to come online, and when it does, it will survey the entire visible sky every few nights, detecting transient events, moving objects, and anomalies at a rate that will overwhelm human astronomers. We'll need artificial intelligence to sort through the data, to flag the interesting stuff, to help us decide where to point our attention. And that's already happening. Machine learning algorithms are transforming how we do astronomy. They're classifying galaxies, detecting exoplanets, identifying supernova, and finding patterns in datasets so large that no human could ever analyze them manually. These algorithms don't get tired. They don't have biases, at least not the same ones we do. They process information faster and more consistently than any human team, and they're getting better. Every year, the models improve, the training datasets expand, the accuracy increases. Within a decade, AI will be making astronomical discoveries that humans wouldn't have found, noticing correlations and anomalies that our intuition would miss. That's exciting. It's also a little terrifying, because it means we're entering an era where the machines might understand the universe better than we do. Dark matter is another front in the revolution. For decades, we've known that galaxies and galaxy clusters contain far more mass than we can see. The visible stars and gas account for only a fraction of the gravitational pull. The rest is dark matter, invisible stuff that interacts with gravity, but not with light. We've proposed candidates, exotic particles, primordial black holes, modifications to gravity itself. But despite decades of searching, we haven't directly detected dark matter. And recently, the constraints have gotten tighter. Experiments designed to catch dark matter particles have come up empty. Observations of galactic dynamics are refining the properties dark matter must have, narrowing the possibilities. Some researchers are starting to wonder if we've been looking for the wrong thing, if the solution is something we haven't thought of yet. That's unsettling. It means our model of the universe, the one that fits most of the data, might be incomplete in a fundamental way. Jupiter itself is part of this story. NASA's Juno mission has been orbiting Jupiter since 2016, sending back data that's rewriting what we thought we knew about gas giants. The planet's gravitational field is more irregular than expected, suggesting the core might be partially dissolved or mixed with the surrounding hydrogen envelope. The magnetic field is stronger and more complex than models predicted, with localized anomalies that hint at dynamic processes in the interior. The atmosphere shows storms that extend hundreds of kilometers deep, far deeper than anyone expected, driven by energy sources we're still trying to understand. And the auroras, the glowing light shows at Jupiter's poles, are the most intense in the solar system, powered by interactions between the magnetosphere and the moons, especially Io, which spews volcanic material into space that gets ionized and trapped in Jupiter's magnetic field. If 3I Atlas is heading toward Jupiter, it's heading toward one of the most complex and least understood environments in the solar system. We've been studying Jupiter for centuries, and we're still discovering new things. Every mission reveals surprises. Every observation raises new questions. And if an interstellar object, whether natural or artificial, is about to pass through that environment, the data we collect could be transformative. We might learn things about magnetospheric physics, about cometary interactions with strong magnetic fields, about how interstellar material behaves in extreme conditions. Or, if the speculative scenarios are correct, we might learn something about whoever sent the object and what they're trying to do. Interstellar objects are time capsules. They carry information about the star systems they came from, about the conditions in other parts of the galaxy, about processes that happen far beyond our reach. Oumuamua taught us that interstellar objects pass through our solar system more often than we thought, that they're out there, waiting to be detected if we have the right instruments and know where to look. Borisov taught us that interstellar comets can look a lot like solar system comets, that the chemistry of comet formation might be similar across different star systems. And 3I Atlas is teaching us that not all interstellar objects fit neatly into categories, that nature, or whoever else might be out there, has more tricks up its sleeve than we anticipated. The philosophical and cultural implications are enormous. For most of human history, we thought Earth was the center of the universe. Then we learned it wasn't, that we're just one planet among many, orbiting an ordinary star in an ordinary galaxy. Then we learned there are trillions of galaxies, each with billions of stars, and that the universe is so vast that even traveling at the speed of light, you could never visit more than a tiny fraction of it. And now, as we detect interstellar visitors, as we find exoplanets that might harbor life, as we deploy telescopes that can peer back to the dawn of time, we're confronting the possibility that we're not alone, that somewhere out there, maybe very far away, maybe closer than we think, are others, other civilizations, other intelligences, other beings asking the same questions we are. 3I Atlas might be just a comet. It probably is. But it also might be the first unambiguous sign that someone else is here, in our solar system, right now, doing what we would do if we could travel between stars, exploring, observing, learning. And if that's true, if even a fraction of the speculative scenarios hold up under scrutiny, then December 19th, 2025, is the day everything changed. Not because of explosions or landings or greetings, but because of data, because of anomalies, because of a trajectory that looks a little too precise to be random. As science evolves, as our instruments improve, as our models get refined, mysteries like 3I Atlas might become normal. We might enter an era where interstellar visitors are common, where we detect them regularly, where each one teaches us something new about the galaxy we live in. Or we might find that this object is unique, that it's an outlier, a one-time event that historians will study for centuries. Either way, the story expands our understanding. It pushes the boundaries of what we know. It forces us to confront the limits of our models and the vastness of our ignorance. And that, more than anything, is what 3i Atlas represents. Not certainty, not answers, but questions. Big, uncomfortable, fascinating questions about where we are, who we are, and whether we're alone. The data is still coming in. The trajectory is still being refined. The anomalies are still being debated. And somewhere out there, moving through the darkness between worlds, is an object that might be a comet, or might be something else entirely, heading toward the largest planet in our solar system for reasons we can only guess at. The universe is stranger than we thought. It always has been. And 3i Atlas is the latest reminder that no matter how much we learn, there's always more. Always another mystery. Always another question. Always another object passing through the night, silent and inscrutable, daring us to figure out what it means. And we will. Maybe not today, maybe not this year, but eventually we'll understand. We'll look back on December 19th, 2025, and we'll know whether this was the day a comet passed by, or the day we woke up to a cosmos more alive, more complex, and more terrifying than we ever imagined. Until then, we watch, we measure, we debate, and we wonder. Because in the end, that's what we do. We're the species that looks up at the sky and asks why. We're the species that builds telescopes and sends probes and writes equations to describe the motion of distant worlds. We're the species that refuses to accept ignorance as a final answer. And if there's someone else out there, someone who sent 3i Atlas on its journey, then maybe they're wondering about us too. Maybe they're watching. Maybe they're waiting. Maybe they're as curious about us as we are about them. Or maybe it's just a comet. Either way, the story isn't over. The data is still coming in. And the next chapter is about to begin.